Are you ready?
Yeah, do I click the mask or no?
It's up to you. Good afternoon, everyone. We will begin the third informal talk of today. Today the topic is slightly changed, and last week we'll talk about the TTBA information and the long-range spin chain. Please welcome.
Hi, and yeah, thanks for the invitation. It's a great pleasure to be here. First time in Korea. Really interesting, many things. So yeah, I mean, I have been invited to give a talk about these models which we call medium range spin chains. So in one sentence, the medium range spin chain is a term that we coined. Maybe it can be called intermediate range spin chain. Normally, spin chain is two-side interacting needless neighbor, and there are also long-range spin chains with arbitrary distance of interaction. So intermediate range is where interaction spans a finite number of sides bigger than 2, it can be 3, 4, etc. But they are integrable and exactly integrable, and we can find algebraic structure. And we have a paper about this, which is like 1 or 2 years old, and this will be the topic of my main talk, like a formal talk, the second one. But here for the first one, I give rather like an introduction why we went to these medium range spin chains, because these medium range spin chains are somehow, so to say, an intermediate step also to go towards the long range spin chains, which we started to investigate a little bit earlier. And actually today I will be talking about a paper which is like 3 years old already, and the archive number is 1911. It's actually a funny number. 11118. Okay. Many ones. And this is a paper together with Eötvös Yang, who might be attending now, and Gábor Takács. The title is TTBA deformation and long-range spin chains. So what we did, we connected these two things, TTBA deformation of quantum field theories, and trying to make something similar to spin chains, making long-range deformation of spin chains. And this will be my topic, but maybe it's an informal talk, so it's rather good to start with a longer introduction, and maybe for experts it will be boring, but okay, I want to give a longer introduction. So the big question, the biggest question that I have in mind is, what are integrable spin chains and what are all possibilities for integrable spin chains? So this is a really big question, but let us think a little bit. So when I mean a spin chain, then chain means we are in one dimension, so 1 plus 1 dimension, so to say, and we have local Hilbert spaces C to the M, so each spin lives in this, where N can be maybe 2 if it's a normal spin 1/2 or bigger. I choose that each spin state is the same, and I have maybe a number of sides which I can put like this, which are placed along a line. Maybe I have periodic boundary conditions, maybe open, maybe infinite spin chain, but often I will look at finite spin chains in volume L. L is length of the spin chain. And then I have some kind of Hamiltonian which dictates dynamics in the spin chain. So I want to find all possibilities for integrability. And in order to do this, we have to have a definition of what is quantum integrability. And this is not easy, and people write papers about it, trying to figure out good definitions. So as opposed to classical integrability, there is no single accepted, well-defined notion of quantum integrability. This is the first message for quantum spin chains. Instead, we have certain properties which are extracted from known cases, and neither of them is all-encompassing. They are good for some models, and for maybe some other models they are not so good. But one of the important characteristics of quantum integrable models is existence of conserved charges. So conserved charges are operators Q alpha, where alpha is an index. These are operators all acting on the full Hilbert space, such that they all commute with each other. So Q alpha commutes with Q beta, and Hamiltonian is the member of the family, so they also commute Hamiltonian. This means that they are conserved during time evolution. But we need more information about this definition, because this is not enough. So first of all, I require that there should be many conserved charges. If we are in infinite volume, then I would require that there should be an infinite set of conserved charges. But the other thing is about the properties of these charges, because we had this talk about many-body localization. It was already mentioned that Actually, if you solve your Hamiltonian, then you can construct the conserved charges easily for even a chaotic spin chain. Because if you figure out what are your eigenstates, maybe with exact diagonalization or whatever method, then you can also construct the projector. So you can look at the projectors An to these exact eigenstates, and they are a commuting set of operators, and they commute with the Hamiltonian. So this satisfies this requirement. So then all spin chain is integrable according to this observation. So clearly, it's not enough to require this.
Is it commuting the projector operation?
Yeah, because
it's vanishing, right? I mean, if you product two different projectors,
it's zero, but zero means commute.
It's trivially commuting.
Yeah.
So.
Yeah, it's really, it's nothing special about it, but I'm just saying that this motivates that we need some more definition here. Okay. And one of the definitions is that somehow the charges should be found before we solve the full model. This is a physical requirement. So that the charges should be more helpful. They should help us in figuring out the properties of the model. And the second is about the locality. Because in physics we have locality, and this should be somehow respected by all of these integrable constructions. So Hamiltonian should be somehow local in the Hilbert space, and charges should be also local in some degree. Now I will not go into all details because there are different types of models where the properties of charges can be really different. So let us start with the so-called ultra-local spin chains, what some people would call it local spin chains. In these cases, Hamiltonian is the following, that it is a summation over sides. I call it X. It goes over integers. And then we have some kind of Hamiltonian density, so operator density H of X. And in the ultra-local case, this is something like, it acts only on two sides. So I denote it like this, it acts on X and X plus 1. So this is a nice needed neighbor interacting model. All important models belong to this class. I mean, most important models, Heisenberg spin chain, Hubbard model, higher rank models, whatnot. So this is the mostly investigated cases. And in these cases, the charges which can be found for quantum integrable models are also local. So they can be written in some extensive form that there is some kind of X again, and the charge density Q alpha of X, where this is a short range operator. But it's not anymore nearest neighbor interacting. It spans more sides, and I can choose a normalization where I say that length or range of this density is just alpha. This is just a conventional choice. So maybe charge operators exist for every integer alpha, maybe just some subset. It doesn't matter for us now. And if I choose this convention, then I can also make identification. Hopefully you can see that maybe Hamiltonian is as chosen as Q2 because it is a two-side operator. And in many cases, we also have a Q1, which is in some cases global spin Z operator or particle number operator in Hubbard whatnot. So these are longer and longer operators. Locality is respected, and there is a well-defined construction and Baxter relation transanalysis how to figure them out. And they commute, and this is fine. So somehow this is one option for quantum integrability, which is a well-defined framework, and we understand it. Now there is a different set of models, which are the true long-range models, and there the structure is a little bit different. So, for example, the famous example is Harding-Shastri model. So in this case, Hamiltonian is still, it is extensive, so it has an operator density, but this operator density is not the nearest neighbor, but it spans over arbitrary distances of sites. And you can write the Hamiltonian density actually as a double sum, so summation over X and Y. And then you have basically I write it like this. Vector product of two dot product of two spin operators at distance, positions X and Y, multiplied by a coefficient F, which depends only on difference. And then actually in Harding-Shastri model, this coefficient is, I think if I'm not mistaken, X this to the square. So it's decaying. So it means that things that bigger and bigger distances are coupled less and less and less. So physically it's local, locally it is respected in some sense, but it's already long range. And in this case, the construction of the higher charges is more difficult. And actually the full thing, they are not anymore constructed. Okay, let's not go into detail. Also, I don't know enough about it. Let's just say this, but they are not as simple. It's more complicated. It belongs to a completely different class.
I have a question. So actually this, differences
Yeah.
is rather arbitrary. For example, in this case,
Yeah.
you can make a linear combination of all these conserved charges to define new Hamiltonian. Okay.
Yeah.
And then this Q alpha is a kind of that term, like a distance between two. Level is alpha instead. So
The one point here is that here we know that there exists one basis of charges which are nice, and you also know that you can construct this basis of charges using a completely local transfer matrix, which is matrix for X operator.
That's right.
And here it doesn't work.
Okay. So in other words, this kind of model has the shortest operator exists.
Yeah.
Side two.
Yeah.
So
And
that
also,
model doesn't have any.
I will come to transfer matrices later, but this is very important that they can be completely local and with a local MPO with small entanglement, operator entanglement, etc. So that is important. And then there are other types of long-range models, which is not like this, but something similar, which is of interest maybe to people in the audience, which are so-called long-range deformed models. So you know that when you go to APCTP Duality and you want to get, well, you want to solve the spectral problem. So eigenvalues of dilatation operator, then you are dealing with integrable spin chains actually. They are higher rank spin chains, and these integrable spin chains are actually long-range deformations of neither neighbor interacting models known from condensed matter literature or integrability literature, etc., etc. And here, what I mean is, we need in the super Young mills, we need to go to planar limit, and then we still have the Hopf coupling. And then the idea is that somehow the Hamiltonian and the conserved charges, what you get in this model, are long-range deformations of some charges and Hamiltonians of this type of class of models. And I will explain what is the long-range deformation because this will be my main topic. I mean, for this informal talk, what are these models, how to get them from known easy constructions, and how to relate them to the TT bar deformation. So this is my main topic. At the moment, my message is just that somehow when we look at these different classes, then this opened up the motivation for our work on medium range spin chain. So I just give a comment at this point. So the medium range spin chain is something similar. Medium range spin chain is something similar. It is a generalization of this one to those cases where Hamiltonian spans more than one side. So for example, h of x can be a three-side operator. So I think x on side x plus 1, x plus 2 maybe. Or it can be four-side or whatever. And then the charges get also longer, but they exist in a very similar structure. So this will be the topic of my second talk, the formal talk, which I was invited to. But I am mentioning this because somehow when we started to think about long-range deformations, then was the idea that instead of the full long-range spin chains like this and this, we should think a little bit of a simpler problem, which are medium-range spin chains. So this was somehow, when we started to look into medium range, then this was like a warm-up example. But also, I mean, I don't know whether I will have time for this, but in condensed matter literature, there is also motivation to look into medium-range spin chains. Maybe in my second talk, I will mention motivation, okay? But for the moment, this will be my main topic for this talk. So I will erase some things and then start over. I want to talk about long-range deformations. And at this point, I can also already tell you that when I mean long-range deformation, I am interested in the general theory. So I do not want to solve n equals 4 super Young mills. I mean, I know that the community wants to solve this one, but for me, other question is more important. The other question is, what is the algebraic structure of possible long-range deformations? What are all possible integrable models? It's much more general. But of course, if it's much more general, then we can achieve less. So if you choose your specific model, which is n equals 4 super Young mills, then you can do a lot because it is very strongly symmetric. There are good analytic properties, etc. And actually, you know, the dilatation spectrum is solved. It is known quantum by quantum spectral curve method, etc. So this is a solved problem. So maybe you can ask, what are then we doing? No, I mean, this is solved, and that's why I'm saying that I want to advance the understanding of long-range spin chains in a more general setting. So maybe we can compute something for ADS-CFT, maybe we cannot. let's see. But I want to return to the old ideas of let's try to understand what are possibilities for long-range deformations which are integrable, which keep integrability. That's my motivation, which also shows that I'm not really from this ADS-CFT community, but maybe you can understand it.
So if I want to comment that this ADS-CFT of long range is still perturbative sense, because this is valid when lambda is less than 1.
Yeah.
Then you can go to the higher order of this perturbation theory, then you can map the spin chain.
Yeah.
But if you go to the range where lambda is bigger than 1, then spin chain concept is not valid anymore. All this, quantum spectral curve, etc., is not coming from spin chain, but from the scattering theorem on the world issue. So.
Yeah, thanks. So I cannot say anything about this. I will be focusing on perturbative regime.
Okay.
Okay, so what is a long-range deformation? So I will choose a different letter. I will forget lambda. For some reason, I will choose a letter kappa, which is our small parameter, it's the deformation parameter. And what I have in mind is I want to start from a known theory, which is a nearest neighbor interacting theory, and I want to make a long-range deformation out of it. Now, let me define it. So long-range deformation, I understand the following, that there should be a Hamiltonian, which depends on kappa coupling or deformation parameter, coupling constant. But it should be such that integrability is preserved, which means that there should be an infinite set of conserved charges on an infinite length spin chain, which all depend on this kappa parameter. And there for each kappa, there should be commutativity. So this means that somehow this Q alpha and Q beta, all of them, depending on the kappa is the same. They should commute, and Hamiltonian should be a member of this family. And we should have the limit that so the limit of kappa goes to 0, or H kappa is clearly the original nearest neighbor interacting model, and the same for the charges. And what's more, I will be a little bit informal also in how I present things here. So I do not know whether these charges as a function of kappa have an explicit solution. Instead, I will be interested in perturbative expansions. Maybe this is not so nice, but it is well motivated, and it's a good theory. What I mean is not so nice is that we don't know, in the cases that we consider, we do not have an explicit solution for actually the charges as a function of kappa. We have good solutions up to first order only, so it's not much. But it's already something, and we have new results. And believe me that it can be defined in a well, there are good definitions, I will tell you. So
can I ask one irrelevant basic question? So here you consider infinite spin chain, and then you think that you have infinite number of conserved charge, but how infinite? I mean, both are infinite.
Yeah. So normally it happens that the length of the charges goes well, it's linear. It's same as the alpha, and then you have each charge until the given length. So normally charges are meaningful until alpha is smaller or equal than L, which means you have as many charges as the volume.
Yeah, that is it. So that means
morally, sometimes you have actually the double of them. So, but the number of charges grows polynomially with the volume. That's my statement.
Okay, so is there some model which has like infinite spin chain and it has infinite charge, but it's not integrable, which is not in quantum integral?
Yes, but these are special theories. Right. It's called Hilbert-space fragmentation. It would be a different different topic when somehow the Hilbert space completely splits into many sectors, but exponentially many sectors. So not like with symmetries. If you have a symmetry, then it's linear in size or something. But into exponentially many sectors which do not communicate with each other, and then you can just construct charges which are some projections to the sectors. And this exists, and they are chaotic. So inside each of the sectors, they are chaotic. This exists. It's a fashionable topic now in condensed matter, but I wouldn't call it integrable, because even in these models, inside the sectors, you cannot compute things. So, okay.
So yes. So the super perturbation theory, order of lambda. I mean, the perturbation order determine the ranging, right?
Yeah.
So here, deformation makes from one loop to few loop.
So
Will you,
I'm coming to this in just now.
Okay.
So what I have in mind is again, what you're asking, I think, is a perturbative expansion in kappa. So instead of just requiring this, I require that it should be perturbative. So I'd say that h of kappa is a summation of n goes to 0 to infinity, and then I would have k kappa to the power of n by n factorial, and then some kind of expansion coefficients this. And the 0th order term is neither stable interacting. And then it happens that I want to look at cases where expansion coefficients which come later have longer range, but finite range. This is important. So this is very important. So when I do the first deformation Hamiltonian can be already, I don't know, 3 sides, 4 sides, but also 10 sides. I do not care, but it should be finite. So this I require. And then I also require that as I go increase n, then the length of these operator densities should grow linearly with n. And this is a requirement. It is somehow nicely agreement with locality, and we see it's happening. Okay. And then I also want to require that the charges also have a similar expansion. So there will be many different indices now, but let me write it out. So from 0 to infinity, kappa to the power of n factorial, and expansion coefficients. Here is an expansion index. And then I want to have commutativity like this, which means that I take 2 expansions for alpha and beta, and then I make a commutation relation, and then I understand that the commutation relation is also a polynomial, at least it's a formal polynomial in kappa. I don't know about convergence, but let us assume that it's convergent, but I'm not proving. It's a polynomial in kappa, and then I understand perturbative integrability, that the different terms in kappa, so for the corresponding different powers, should be 0, 1 by 1. So this is perturbative integrability of long-range deformation. It's a good sense of integrability, and also for physical quantities, you can show that it shows up until which order it is integrable. For example, you could do that. If you have let's say something like this, and if you have commutation up to all orders, then you could also do that. You forget higher orders. So you add, for example, only first order or second order. Then the commutation relation will not hold exactly because you throw out the rest, but it holds up to a given order. And then you can investigate physical properties of that Hamiltonian, and then you see that it is very, very close to an integrable, and in a perturbative sense. So it makes sense completely to have this requirement. And then you also see that when you do this.
I'm sorry, you are saying that statement claims that Q alpha n commutes with Q alpha m?
No. There will be sums.
Okay.
And then you can try. So you get some system of equations, and maybe you want to solve them, but it's very difficult, so it's not easy. But yeah. And then this is the form what is happening in the ADS-CFT spin chain. Where these terms are given by their field theory computations. So, or at least for the Hamiltonian. And then there was a paper or a series of papers some time ago by Balazs. Let me check the reference, because I don't remember precisely. Barkier, Weisert, and Löbberg, series of papers, and maybe I can mention one paper which is very nice to read. So the archive code is 0902.0956. And so as you can see, this is from 2009. So it is already a 13-year-old paper, which we went back to, and we started to investigate again, taking up the line of thought that they were doing. And in this paper, they were figuring out what are all possibilities for long-range deformation. So they have some kind of solution for how to do this. They have some procedure for this. And we went back to this procedure and we made additions, and I think maybe I might say a better understanding of what their procedure is. Because we pointed out that in some cases their procedure is actually the same structure as TT bar deformation, just with a little bit different operators. So this is what I want to say. And this is a little bit, or actually very surprising, I would say, because I mean, this paper was there and people knew it, but they didn't connect to TT bar, which is also very fashionable. So it's a little bit surprising that it was not done. And I should also say that roughly at the same time when we put this online, there was also a parallel paper by Alessandro Spondrini and collaborators with the same results, absolutely the same results. they told me that they had it, but for some reason they didn't publish, and I believe because the difference is 1 or 2 weeks between the two papers. So we were first, but they had it at the same time. We were just quicker to archive somehow. But they discovered the same, yes. And in order to tell you our results, first I need to talk a little bit about the results of this paper. In this paper, they figured out the long-range deformation in maybe I can say canonical form, or I don't know, lockstep form, right? I don't know what name to write. So the idea is to, I will delete it. The idea is to have some kind of operator X, which will actually also depend on kappa, and X is generally non-local. It's not a local operator, which will generate maybe I can say unitary transformation, at least formally unitary transformation, which will transform from our original spin chains into the kappa deformed spin chain. So there is some kind of equation for evolution in kappa, which is the following, so that d per d kappa of, let's say, Hamiltonian of kappa is, maybe I will also need a I here, commutator of x kappa with h kappa. And it's a strange, so this is like a Heisenberg time evolution, if you would call this the Hamiltonian and this some other operator. But the strange thing of this equation of motion is that actually the x kappa, the generator, will also depend on the Hamiltonian and on the charges. So it's a little bit complicated. But formally, you can also say that if you integrate this equation, then formally you can say that h kappa is somehow the transformed version of the h0. By transformed version, I mean this formal operator kappa x. It's actually, if it would be constant, it would be like this, but otherwise it will be a time-ordered integral, etc. So, I mean, this is somehow in not precisely this one, but something similar. Okay. If x would be constant, then you would have this one. But if you look at this kind of equation, then you would think that maybe it is too trivial. I mean, is there anything interesting happening? What do I mean by it? One possibility for this x operator is that you can choose this x operator to be also a local operator, constructed from local Hamiltonian. The one possibility is that you choose x to be summation of x and some O operator x. So this should be a local operator, short-range operator. Now, in this case, this equation makes perfect sense, but this is like a singularity transformation in the Hilbert space dictated by this. It's like an extra Hamiltonian density, symmetric transformation by Hamiltonian density. And if you work out the properties of this transformation, it will be just like this. So you can expand it into a power series, and then you can do the same symmetric transformation also for the charges. They commute with each other. You can also expand the charges into a power series, and everything works. But then you would say that maybe this is too trivial. No, I mean, we are doing a singularity transformation with a local operator. So this is like a basis of change of basis in some way, but physically not much changes. And you can see that physically not much changes when you do this, because if you do it in a finite volume, then the energy spectrum is not changed. This is very important. If you do this specific kind of thing with this operator. And then maybe you would say that this is the same theory. I mean, we are just choosing a very wrong basis for the theory, but it's the same theory. I mean, the energy spectrum is the same. So somehow we want to disregard it. I mean, this is maybe too trivial. Maybe I don't care about it. I would want to have something which is more complicated and something which actually changes the finite volume spectrum and it changes transport properties a little bit. So that we know that the theories are genuinely different after that long-range deformation. This is what is interesting. And then already from this example, you can figure out that maybe we need something worse than a local operator for the singulated transformation, where locality is a little bit more broken for this X. And this was the solution of Balazs and collaborators, and they came up with two different solutions. Where should I write? I mean, maybe if I write here, is it visible? No.
It's visible.
Also for, they changed. Oh, very good. So there are two types of things that they found. One is a boost type of deformation. Another one is the bilocal type of deformation. And these are just names, but let me write it down. So for the boost type of deformation, one possibility is that you choose a specific charge index alpha, and then you say that your X, let's say put it like this, at kappa, is the following. You have a summation over X where you put here operator density of alpha multiplied by X. So it's like a boost operator really. And this should be also dependent on kappa. And then this thing defines your equation of motion evolution in kappa, because you plug it into this equation, then it tells you what is change with respect to kappa of the Hamiltonian and the charges. But then this X already depends also on the solution. But it's a well-defined equation of motion, at least perturbatively, it's good. And this is non-local in the sense that what is non-locality here? So it's not all things like operator norm and things like this, it's not an extensive operator because you produce here this X.
What happened for this periodic boundary condition?
Now this is gone. And it's a very good question.
So this is an infinite change.
Yeah, infinite change. Yeah. And this was the biggest question for us. How can we do this deformation in finite volume? So this is our one of the main motivations. Very good.
So you
question.
can do.
Yeah, I mean, we are progressing. It's not, yeah. Actually, my recent work of Tamás Gombor is one of for this. But this is very recent, yeah. So the other possibility is the bilocal deformations, where X of kappa is the following. I have a double sum. I say X is smaller than epsilon, and then I choose actually two indices, alpha and beta, and then I multiply Q alpha kappa of X and Q beta of epsilon. So the charge, it's like it's almost like a product of two extrinsic charges, but like one half of the products, because I have this restriction X smaller than epsilon. And then you can try to work out what happens with your theory. And in this paper of Balazs and collaborators, they show that there is a clear physical effect of the boost deformation and the bilocal deformation. This will somehow change you the propagation of your particles in Bethe-Ansatz picture, and this will deform you the S matrix. So far I didn't talk about S matrix or Bethe-Ansatz. Maybe later, if I have time, I will come to this. So this is just somehow a comment. So this changes S matrix, this changes propagation. Okay, maybe I write. So the standard Bethe-Ansatz equation looks like this: that quantization equation in finite volume is that e to the pi, I don't know, some in the particle index k times volume multiplied by product, I don't know, L not equal to k and S matrix depending on P, K, and PL. And this is equal to 1. This is Bethe-Ansatz quantization condition. And then my statement is that if you do boost, then you change these parameters a little bit. And if you choose do bilocal, then you deform this one a little bit. And basically, these are the possibilities. And of course, I should give more definition what I mean by this. And there is no, maybe at the end I can come back to this. And the claim of Balazs' paper is that all possible long-range deformations which satisfy these requirements will be of this form. Either it is this trivial deformation, or these two, or what is also possible, what Chandri mentioned, that I can take linear combinations of charges, and it also gives you something like this. And this is not proven by Balazs, as far as I understand. It was more like an observation. So they went to concrete spin chains. They considered this problem and commutation relations, and mechanically they solved it and looked at small distances and small possible cases, and they observed that this is all what is there. But as far as I know, it's not rigorously proven, but it's believed to be true. So this was known, and one comment. So if we actually go to the spectral program of ADS-CFT, then we need to take linear combination of these guys. Because here I select the specific alpha, here I select the specific alpha beta. I can take any linear combinations for the X, and then it generates a complicated evolution of motion. And this is believed to be working for ADS-CFT. Right, and now I can come to our results, what we did. And in one word, what we proved is that this bilocal deformation has essentially the same structure as TT bar deformation. This is the statement. And I don't know if this is surprising to you or not. So maybe people know more about TT bar. So when you just look at this and the deformation equation, where is it? deformation. Does it look like TT bar to you? I don't know.
So when
Yeah.
you say that this looks like TT bar, means that if you deform by this by local,
Yeah.
then this asymmetrics gets extra CDD factor.
Yeah. But it's even more. I can show it on operator level. Because we know one thing is that for TT bar, we know that it deforms by CDD factor, as you mean. But I can also show on the operator level what is the correction for Hamiltonian, that it is similar to TT bar. Not the same. I will explain now. So, but at least I am confirmed that it is not completely trivial. And then people didn't observe this earlier. So, so then let's just start with TT bar then. So I read this one. There will be many definitions. So, okay, what is TT bar? I mean, people in the audience know much better than me, but let me just write something. So TT bar is formal way of writing an operator, which is constructed from energy, what is this, momentum tensor. And this is in complex coordinates, but if we go to normal Minkowski coordinates, then this is determinant of matrix T mu, which means that this is like T11, T22 minus T12, T21. And then you add this to the action, as far as I understand. It's a very special operator, which can be defined in a meaningful way. And let me write a different idea for this combination. Different idea is that I want to understand it using language of charges and currents. So the T energy momentum tensor in normal coordinates is maybe the following, that here I have density of energy, this is the standard thing. Maybe here I have a current of energy. Maybe here I have density of momentum, and maybe here I have current of momentum. So these are the standard identification. Maybe these two is exchanged normally, I don't know which is which. But in any case, when I do this combination, then using this language of identifying what is what, okay, and this is time, this is space, so to say, time and space. Then I get, what do I get? So energy density multiplied by current of momentum minus, I can choose anything I want. For example, current of energy multiplied by density of momentum. So it is antisymmetric combination of current and charge operators of two charges. Because we have two conserved charges, which is somehow underlying this, energy and momentum. And the idea is already in quantum field theory, you know much better than me, that somehow this antisymmetric combination appeared in other types of similar deformations like GT, I don't know, these kind of things, where you choose just a different charge, not energy and momentum. And we will see, what we will see is that this deformation generates us deformation terms for the Hamiltonian and also for higher charges, which are of this antisymmetric type, where instead of energy and momentum, we really just have these two charges of the spin chain, Q alpha and Q beta. This is the short answer. And this we need to prove, but it's actually not a very difficult proof, but we need to go there. And this was our big observation. And the first important comment is, before we go to computation, is that here in normal quantum field theory, we have Lorenz invariance. So these things are very closely connected to each other. But now here we have a spin chain, and on spin chain you don't have Lorenz invariance. On a spin chain, a certain charge and a certain current associated to this charge are two completely different operators. I mean, in Lorenz invariance, they are just components of the same two vector, they transform into each other. But we don't have it. In operator level, you sit down and they are just different operators, completely different. And you don't see any easy way to connecting them. So it's a little bit different. So we need, okay, so in order to show something like this, what we need is we need to talk about current operators. Because so far, with what did we have? So far, we had Hamiltonian and charges, but we didn't have currents yet. So let us then define current operators for the spin chain. Now, this is our next task. So first, let us not talk about these deformed things, but just the simple things going back to the original starting point. In the original starting point, we knew that, for example, global Hamiltonian commutes with all global Q alpha. This we know. But then how do you define current operators? So you look, when you want to have current operators, then you can think, for example, that you want to look at your system and you want to find out what is the charge contained in a region which goes from x1 to x2. And then if you want to figure out what is the time dependence of the charge contained in this region, and then you will set up a continuity equation. And this continuity equation, just like in classical mechanics, gives you a definition of charges. So in classical mechanics, what you would have is that you integrate the charge density from x1 to x2, and then you say that the time dependence of this is given by what is inflowing here minus what is outflowing. So this is something like J alpha at x1 minus J alpha at x2. And this is classical continuity equation. It defines you current operators. You can also, of course, you can also do it locally. So this is integrated version, but you can write a local continuity equation with derivative, space derivative. Now we want to do the same thing in our quantum spin chains. So in our quantum spin chain, the integral is replaced by a sum, and otherwise this time derivative is replaced by the commutator with h. So in our integrable spin chain, the definition is the following: that we want to compute time evolution of, in the simplest case, just the local density. So when I say, for example, I choose x1 and x2 just to be nearest neighbor sites, for example, then for this density, I can write it as there will be some I here as some kind of. So let me check what is the definition in our paper. So the definition is that here is I, this is Heisenberg equation of motion, and then this is J current operator at x minus current operator at x plus 1. So this is operator definition of currents. As soon as you have an operator density for charge, you can figure out what is this operator. And then the choice that I put in x and x plus 1 is just arbitrary, but we have to have a choice. And let me also introduce something more general. So this is time evolution under Hamiltonian. But you know that we have many conserved charges, so Q alpha, Q beta, etc. So we can also consider time evolution under other charges, and they define new generalized current operators. So what I mean is I can take the commutator of some Q beta with my chosen charge Q alpha, and then this defines me generalized current operators. And for this, we chose the following convention, that this will be an operator with two indices, positioned at x, and this position at x plus 1. And we just remember that first index describes me what is the charge density, which is evolved, and the second index describes me what is the global evolution operator. And we will use both the actual current operators and also the generalized current operators. And one more formula which is perhaps useful is I can think about this situation, but I can push this x2 out to infinity. So I can say that I push x2 to infinity. So I consider the problem of what is time evolution of charge contained in a half infinite segment. And for this half infinite segment, what will happen is that somehow I can push these terms out to infinity. So for example, I mean, instead of this equation, I will put it here. I will have I times Hamiltonian commutator with summation over Q alpha x, and x goes from, I don't know, y to infinity. And then this will give me, if I'm not mistaken, just a single j position at y, because the other one is pushed out. And this is just a formal definition, but it's very good because it's useful for our computations. And also, if you want to do it on an operator level, actually the computation is good because you will see that the two things will be separated from each other, and you can easily recognize what is the current operator. And then the idea is to sit down and take the result of the Weibert and collaborators paper and figure out the commutators at least to first order. So do we have still the equation? No, I deleted it. So I will put it here then. So what was the deformation equation? It was that kappa derivative of, for example, Hamiltonian was commutator of x of kappa and the Hamiltonian. And now I want to look at lowest order terms. So I want to compute the first correction term, which is simply just given by x, so to say at 0, commutator with h, so to say at 0. Maybe there was also an I here, I don't know, if I'm not mistaken. So I want to compute first order deformation term with these two types of x's. So this x and this x. And the idea will be to write these expressions such that they contain something similar to this one. Because then we can see that the current operators emerge. And then the trick is that, for example, if you have the boost operator, the trick is you write this x in a way that how to explain it. So for example, imagine that you have your this is your x, which goes from 0, 1, 2, etc. over all integers, and then you want to figure out how many times you add the q alpha position at x. And at 0, you add it with 0 coefficient, at 1 with 1 coefficient, at 2 you add it with how to draw it. Sorry, this is nothing. Sorry. So at 1 with 1, at 2 with 2, at 3 with 3, at 4 with 4. And then what I mean is that you do a resummation where you add things. So you do add this infinity, and then you add this infinity, and then you add this infinity. And each of these infinities will be a half infinite summation. And for this half infinite summation, you can run this formula. And then you still have a summation over the half infinities. And from this, you can already observe that when you do this commutator with this boost, then actually this will be equal to summation over sides j alpha of x. Maybe with a different sign, I don't know, but it can be figured out. So this was a result that was in one of my papers a little bit earlier, before the TT bar paper. So the message is here that the boost deformation is generated by the currents. So what happens for the second type of thing? What happens for the bilocal ones? Now, for the bilocal ones, we also need to have some kind of formula where we would have these half infinite things. And then the idea is very simple. So how should I write it? I did it. I go here. The idea is that I take the x, which is a summation over x smaller than epsilon, q alpha x, q beta at epsilon, and then I write this as a summation over x going from, I don't know, minus infinity to infinity, and then a second summation over, how should I put it, epsilon goes from maybe x plus 1, in this case, to infinity, and then you can take out this q alpha x here, and then you can put this q beta epsilon here. This is just a rewriting. But when I do this commutation, then it will be an operator product, of course, but then you do these tricks of commutators, etc., etc. And at one point, you will need to take a commutator with this guy and the Hamiltonian. And because you do this commutator tricks, there will be actually two terms. And when you collect everything, then you get this CT bar-like term. Let me get the final good answer. Which is good, including signs. Where is it? Sorry. Maybe I will write it, and maybe it's not correct to sign, but otherwise it will be correct. So in this case, H1. No, I need it because there is an important technical difference. Sorry, I need to find a good formula, but it is a mistake that I didn't look it up. Yeah. So the good formula is, because the operator splitting is actually important. So there will be some j. This is alpha positioned at x, q of beta positioned at x, minus q alpha positioned at x, and j beta positioned at x plus 1. I hope I hope it's good. It's still not the good formula what I have in mind. But anyway, you see that it's an antisymmetric combination. Operator product is important, so it is really in this way when you do the computation. So one time J is second and one time J is first in the operator product. And there is this difference which I cannot explain, but in this particular case in the spin chain, it is really like this, that we have x, 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 and x plus 1. You can choose other conventions, so there can be some changes, but there is no possibility to have x, 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 x. I don't know why. Maybe it's not meaningful, but on a technical level, you see that something like this will happen. So you can shift it around a little bit. But then this also means that on the spin chain, we have a precise definition for this point splitting. I mean, this is what we need to do, and that's it. And then, again, what I mentioned at the beginning, so this is of the form of the PT bar combination, because you have charges and currents. And this was our main result in our paper with Eötvös and Gábor Takács. And what we also did is we looked at first order deformations of not the Hamiltonian, but some other charge. So the idea is that, let me just, so now there will be many indices, because bilocal deformation has two indices, alpha and beta, which parameterize with the deformation. But then I can also look at time evolution of another charge, a third charge, Q alpha. So I can compute what is commutator of X and some Q gamma with third index. And this will be a peculiar combination, which I will write. This is the following. It will be given by generalized currents. So this is J alpha gamma X and Q beta X minus Q alpha X and J beta gamma X plus 1. So this was the reason why I introduced the generalized current, because we will need to have these types of commutators also with some rearrangement of indices, and then generalized currents appear. So what did we, so this is the main result, and we pointed out that long range deformation is on the one hand side there is this boost type of deformation, okay, it is given here, and the second type is that it is of the same structure as TT bar. Okay, so what does it mean? I mean, maybe I have 10 minutes from this talk, so not so much, but it's okay. So what does it mean? I mean, TT bar is a very specific deformation of this type in QFT, which means that there we have energy and momentum as charges. Here we have two arbitrary charges, alpha and beta. So can it be exactly the TT bar? And my answer is no. The problem is that in TT bar we have energy and momentum as the two charges, but there is no momentum on the spin chain because it's not translational invariant. So it is invariant with shift, but that's different. It's not a local conservation law, and this is a problem. And this is an unsolved problem. So somehow the actual TT bar deformation for a spin chain is not yet found or not yet worked out. Because I don't know how to do it on a discrete system if there is no local P. But other deformations like I don't know. I mean, you can tell me, but if I forget about P and then I choose energy and some other charge, this is perfectly fine already. So this we can do.
So this is like JT bar, or
I think yeah, but I don't know enough about the JT bar, but I think yes. But then definitely P should not be there. So that's one thing. Another thing is that this is nice, but we have another result which we call hard rod deformation, which is a little bit similar, maybe closer to TT bar, but it's still not the same thing. There's not enough time to talk about it. It will be topic for second talk, but the hard rod deformation is the following: that normally when we have a spin chain, then maybe we have particles which propagate on the spin chain, and we have now a well-defined way, at least in certain examples, it's not completely general, to make this thing into a hard rod. So we can make, from one particle, we can make a pair of particles such that they propagate, and the interaction between pairs will be the same as interaction between single particles here. So this is like a volume changing of the particles, and we can do it on the level of Hamiltonian and charges, etc. We call it hard rod deformation of XXZ spin chain. It's also very interesting. It's also similar to TT bar because it's volume changing, still not completely the same, but somehow similar. Okay, and this what we do here is on a technical level different from what happens here. And I think the only thing is that indeed momentum is not a constant quantity on the spin change. So that's about the interpretation. And that's physical interpretation. And then also I should mention physical consequences of these deformations. So there's no time to make derivations, but again, I can tell you that what happens here, that if I do the deformation, then I can keep rapidity variables. So normally we have rapidity variables. Momentum is characterized with rapidity variable lambda, and beta ansatz is nice because in terms of lambdas, the S matrix will be of different forms. So in nice beta ansatz solvable systems, if you choose the S matrix and you rewrite the momenta in terms of rapidity variables, then normally it is, so to say, Loránd invariant. So this will be lambda k minus lambda L. So it's nice variables. And then it turns out that the beta ansatz picture can be held more or less when you do these deformations. It's just asymptotic beta ansatz. It's not exact infinite volume, but with a good approximation, it holds such that for this guy, you will need to add something of the charge mean values, or local charge mean value. Now I'm rushing a little bit because of time problem. Yeah, please excuse me. Now this will be a little bit rushed, but let me say that if I have a beta state consisting of some rapidities to lambda n, then to this beta state I can define charge mean or find charge mean values. And for charge mean values, I will use a function h alpha of lambda, which is single particle charge eigenvalue. And then it turns out that if we do these deformations, then for boost deformation, what happens is that P lambda gets modified to P lambda plus kappa times H alpha of lambda. So on an operator level, we deform with the current, but on the level of beta ansatz wave function, the momentum gets changed with the charge eigenvalue. And then if we do the bilocal deformation, this TT bar like deformation, then the F matrix gets changed, and F matrix as a function of lambda and mu. It's not of difference form anymore, so it gets changed by the CDD factor, and the CDD factor is the following: so e to the delta lambda mu times the original S, and this delta is an antisymmetric combination, so H alpha of lambda H beta of mu minus the other one, so minus H alpha of mu and H beta of lambda. Maybe a different sign, I don't know, but it can be figured out. So again, antisymmetry, but now antisymmetry for the charge mean values, and this deforms you the S matrix. And okay, last 5 minutes. So also a very big question is, how general are these long range deformations? So if we pick some initial model and we do long range deformations, but not just to first order, but to many orders, and maybe we sum it up, can we go to arbitrary spin chains, arbitrary integrable models? And there is a paper by Benjamin Doyon, where he claims that we can do this, and it's a very big claim, but very difficult to check or to figure out whether it's a good claim or not. So Benjamin Doyon claims that all integrable models are basically this type of deformations of nearest neighborhood spin chain. This is, or actually all integrable models which are local in some sense, that translational invariant, and there should be a good operator density, but it can be spread out. But this is a little bit problematic to me because sometimes particle structure can change, so sometimes bound states, I don't know what. So many things can go wrong. But at least for models which are somehow close to a given integrable model, then we believe that these deformations are enough to construct all of them. So in the space of all possible theories, if you pick a nearest neighbor model and you want to figure out somehow all models which are somehow close to it, then with linear combinations of these deformations, you should be able to go to them. This is my statement, but it's not proven. So this is very vague, but just a general feeling. So where does this feeling come from? It comes from the fact that looking at the beta ansatz, I mean, these deformations for CDD factors and then the momentum are enough to generate all types of beta ansatz equations. This is the idea. So these functions are general enough so that the linear combinations of these and then integrating them should give you a change from any S matrix to any other S matrix. Roughly speaking, this is the idea. But of course, what does it mean to have big changes? So then, as I mentioned, particle structure, particle content can jump. So it's a difficult problem. Yeah, so this was one final conclusion, and I wanted to say something else. And another physical message is that this game that we played here, this was playing with half infinite spin chains, and all of this construction is rigorous for infinite case. And here I made a really big jump. I went very briefly to finite volume situation. You can ask, is this meaningful or not? And it's an important question of how to put these things into finite volume. And when does it exist? And this was our main motivation to look for medium range spin chains. And for medium range spin chains, we understand it. And for long range spin chains, this is an ongoing project where my postdoc Tamás Gombor had a paper like a couple of weeks ago, where he made substantial progress, but it's not solved. So the message is that we believe that all of this can be done in finite volume, meaning that we can also define eventually exact quantization conditions for long-range reform model, not just asymptotic beta answers, but exact, including all wrapping corrections. But so far we can only do it perturbatively at first order. But Tamás actually had some results for wrapping corrections, so I really suggest to check this paper also. And that's very recent. And I don't have time to do this. This was informal talk, and second one will be about meeting range. Thank you.
Later question.
So one question, and then maybe you said this, but the original motivation was, you said at the beginning that the first deformation you considered was too trivial because it doesn't change the spectrum, so you want to do this one that does, and then you wrote down the S matrix. Are there examples where you can get the spectrum, say by beta on outside of the S matrix, or just directly, where you know the deformed spectrum associated with one of these TT bar like things?
What do you mean? So you want to have cases where you check the beta ansatz equations, or what?
I'm wondering, is there an analog of, say, for a TT bar deformed field theory, you would write down and say, if I have the deformed spectrum, I can TT bar deform, and I write down a formula for, or say, the undeformed spectrum, and then I write down a formula for the deformed spectrum. Yeah. And then I was wondering, since, I mean, you have, in some cases, expressions for the deformed S matrix here, right? So you can imagine doing some TBA type analysis and using those to get the deformed spectrum with this thing. So has that been done as well?
Not that I know of. But so again, what I mentioned, if you go statistically to area CFT, then this is dilatation spectrum of or area CFT, and then quantum spectral curve defines you this spectrum. But for these other types of deformations, it has not yet been done. I mean, Eötvös had some papers where he does something similar. So maybe, I don't know if he's in the audience. So I don't know these details very specifically, but indeed, some TBA should be done, and is there with a little bit, huh? Is there? Maybe he wants, I don't know. If he wants
okay. Sorry, can you repeat the question? It's a bit unclear.
Yeah, my question was, is there an analog of the statement that for a TT bar deformed theory, if you know the undeformed spectrum, you can write down a formula for the deformed spectrum? And in this case, it looks like, in principle, you should be able to take your deformed S matrix and do TBA to find a formula for the deformed spectrum in the spin chain version. So I was wondering, are there any, say, even toy examples where you know an explicit formula for the deformed spectrum using this spin chain version of TT bar?
Okay. So that, yeah. So I think the Berker's type equation you can always write down. That's not a problem. And in the case of TT bar deformed CFT, the fact that you can solve it is because you know the dependence of energy on the length L. That is simple because it's like C divided by L. So you can solve for the spectrum and get a square root type of thing. And if you want to play the same game, say even in a massive integrable field theory, then you don't know the dependence on L, and the things become difficult. So of course you can solve TBA and get some result numerically. Now in the spin chain case, it's the same. The dependence on the length is complicated, but you can always write down the flow equation, and then you can try to find the deformed spectrum by solving the flow equation. Yeah. Numerically, yes. And for the Lieb-Lidinger model, if you take some C goes to infinity limit, so this is a non-relativistic model, then you got something like non-relativistic fermion. And in that case, you can also get a explicit deformed energy, and that has a cubic 1/3 root, something like that. Yeah.
Thank you.
So in addition to his question, so this is, you're talking about energy spectrum.
Yes.
But can you do some spectrum of other conserved charges, higher conserved charges?
It should be similar, pretty similar, yeah.
But from TBA type formula, you cannot get it because TBA gives only energy.
I mean, no, you can
So-
modify the OTBA computation, you can modify it, I think. Also,
Including the other charges?
Yeah,
So similar type of this Balazs type formula.
well, maybe, I mean, similar to TBA, so this rest energy, rest charges, these kind of things exist. But, I mean, maybe you have too much field theory in your mind. I mean, now I'm thinking really about the finite density situation in spin chain, that it is good.
Yeah, in field theory, I think it's still difficult problem, but in spin chain approach, because since you're introducing this 2 alphas and so on, maybe you can get some.
Yeah, because in spin chain there is not so much difference between energy and other charges. In field theory, clearly, because Hamiltonian is in the cross channel, the translation operator in space, so then we know that it is very specific. But here, I mean, Hamiltonian is just as good as any other charge. It's just the other flow, unitary flow. It's not selected by any symmetry that Hamiltonian is the only good charge because it's symmetry.
So are we at the discussion time now?
Yes.
Yes, like,
I can make some comments on this question. So I think in the spin chain case, yes, you because the spectrum of these higher conserved charges, they are given by beta roots, and then we know what is the deformed beta equation of the. So you can either do it perturbatively, namely you start with some known solution of beta equation, then you can solve the deformed beta equation order by order in lambda, and then you plug in the expression for the charge, then you get the result explicitly order by order, or you just solve it numerically. Say you know the original solution, then you tune like lambda very small, and then you do iteration, then you can find some solution that is at finite lambda. But a funny thing which I found in doing Lieb-Lininger using this approach is that, again, it depends on the sign of lambda. And in one case, when you tune the lambda a little bit too much, then you have some weird spectrum. You have some like complex spectrum, and similar in the CFT case. So I think this problem may be worth some more work, just to numerically see, is there some critical value where this lambda gets too big, then everything just becomes nonsense? And what about the other sign of lambda, whether things make sense? And you can also do this like for thermal partition function and so on. You can find the Hagedorn temperature and so on.
Right, that means that there is no like a simple formula that just size is renormalized.
Yeah, it's not, because the energy you see in the other cases, the dependence of the energy on the size of the system is rather complicated. Well, in the CFT is very simple. So that's why you just redefine it. Yeah.
any other question or comment? In the online audience, is there any question or comment?
So why do you call it boost operator?
I mean, because normally in the normal Lorentz boost is also this form, no? I mean, and it's also the effect what it does that it changes the momentum in a little bit, so.
Mm-hmm. Yeah, but usually in relativistic quantum field theories, the boost operator, when you commute with the charge, it gives back the same charge. And somehow in the spin chain, it's kind of different, no?
I mean, yeah, but it is different because you I think it has to do with these relativistic invariance, and the charge and currents are two different things. But maybe if you do it properly, then it would become the same. So because in Hamiltonian it's changed with the current. But wait, is it true what you say? I don't remember now.
Yes, I mean, if you use a spin S charge, this means that when you commute with the boost operator, Lorenz boost, then it's an eigenvalue sort of the charge of the boost, no?
Mm.
Yeah, but I mean these are not so. Yeah, but what you have in mind are the eigenvalues in light cone coordinates. So this is like
Yes,
E plus
yes.
minus P. But when you commute boost operator with E, then I think you get P, or then the other way around. No?
There's a simpler answer, which is we inherited this terminology from Nicholas' paper, who inherited this terminology from some earlier papers in the 80s. So we don't know precisely why they call it boost. It's similar. Yeah.
So Eötvös is right. So you know that there is a paper by, well, going back to earlier days of quantum integrability, really in the 80s, so spin chain language by Badati also, he also called it boost operator for spin chain, this sort of thing. So, but because it's the same, so.
I think it's a good answer that it shifts the momentum. I'm happy with it. Yeah.
And somebody also has a paper called Lorenz invariance of in XYZ spin chain, but I forgot who wrote this paper. Maybe who was it? But you know, they played with this thing, and of course it's not Lorenz invariance because it's spin chain, but they call it Lorenz invariance of XYZ spin chain because they see these kind of things happening. No, these kind of things. So I should look it up. Who was this? Either one of the Japanese guys or I don't know. Okay, I can find it. Sorry, in the break. Yeah.
So Jolie, what time is it in your place?
I'm in UK, 5 o'clock in the morning.
5 o'clock? Really?
I mean, you start at 5. I'm in the afternoon. This discussion starts at 5 in the morning.
UK is like earlier.
Well, I hope you had enough coffee.
Not yet.
So please check my email to you.
Okay, so is there any other question or comment? If not, let's thank the speaker again.
Okay, great. Balazs, are you ready?
Yeah, thanks.
Okay. So hello, everyone. Welcome back to the afternoon session. So our first talk will be, again, Balazs Pozsgay, who will tell us about further interesting things about medium and long-range integrable spin chains. So Balazs, please.
Yeah, thank you. So first comment to Zoli's question about boost operator. So I found a paper, it is by H.B. Stecker, and it's from 1986. Coordinate transfer matrices and Lorenz invariance on a lattice. This is what I mentioned. It's good to check it out. So he claims that coordinate transfer matrices do this.
Yeah,
it's very similar. I will not go there. But just, yeah. And let us go then to these medium range spin chains. And let me then summarize what I want to do. So the previous talk was a little bit of motivation. What were the open questions? What I mentioned at the end. One of the most important open questions is to go to finite volume, because you remember I had these constructions with these half infinite things, etc. And this was really truly in infinite volume. And now if you wanted to put the same Hamiltonian somehow to a finite volume, then there are these so-called wrapping corrections. One of the problems with wrapping corrections is why does it arise? Because long-range deformations means that for the Hamiltonian, you need to add longer and longer pieces eventually if you want to guarantee integrability to all orders. And if you add longer and longer pieces, eventually, in a finite volume, you will reach a stage where somehow periodic boundary conditions. So the deformation term already wraps around the volume, and then the operator ordering is somehow not clear anymore. So it's not so clear what to do with periodic boundary conditions when the deformation term already spreads all over the spin chain. This is the most serious problem, and we need to deal with it. And this has been a problem for a long time in ADS-CFT. Now, quantum spectral curve solves the problem with independent methods. Nevertheless, we want to understand what can be done with integrability methods. So this is our key motivation. This was my motivation, honestly, for me personally, 2 or 3 years ago. But then there is also different motivation, which I want to talk about a little bit in this part of my talk. So also from condensed matter, there is motivation to look for medium-range spin chains. So as I said, medium-range spin chains is the following, that I have an operator density, h of x, which maybe spans 3 sites, maybe 4, maybe 5, maybe 6, but finite. And it should be, so hx is, for example, it should be acting on x plus 1, x plus 2, or maybe also x plus 3. And as opposed to the previous case, what I had in the previous talk, now this should be integrable already with this range, which is fixed. Because previously with the long range deformation, what we had is we were taking a Hamiltonian, we were adding terms which are longer and longer eventually. But no, here it's, maybe you can say we stop, or maybe you can say these are completely independent models. So actually, in my talk, I want to forget for a moment this connection with long-range deformations. Instead, I want to look at these models without deformation parameter. So just the models themselves. Maybe they have coupling constants. Of course, that is allowed. Or maybe multiple coupling constants, but I do not want to think them as long-range deformation of something. So it's just models on their own right, or in their own right. I don't know English. But anyway, so you understand. And okay, motivation from condensed matter. So in these kind of applications of integrability to condensed matter, people want to look at transport, for example, of conserved quantities and describing transport. I mean, if you have integrable models, then transport is typically ballistic. Because these conserved charges. You can have ballistic currents, and this is very unusual. So real hallmark of integrability is ballistic transport, but you can also have diffusive transport and more exotic things like subdiffusive, superdiffusive transport also. And when people look at transport, then there is a new theory called generalized hydrodynamics. I don't know if you heard about it or not. So it is a hydrodynamic theory based on Bethe-Ansatz description of these models. It's really hydrodynamics, but it involves the exact Bethe-Ansatz description of your models. And this is very good theory, very successful, but it's not rigorous, which means that you cannot derive it from first principles. You need to make some kind of assumptions which are usually made in hydrodynamics. And maybe you would want to prove this hydrodynamic theory, at least for certain selected toy models. And for a generic integrable model like Heisenberg spin chain is not good enough because it's too complicated. So even in Heisenberg spin chain, you cannot prove hydrodynamics. You cannot prove predictions of hydrodynamics. Predictions seem to agree with numerics, so people believe that it is correct. Some parts are proven, but not all of it. And maybe if you want to prove it, then you would consider models which have a more simple structure than x66 Heisenberg spin chain, xz Heisenberg spin chain. So we want to select toy models. And then in the recent years, in the literature, many new toy models showed up. And the toy models typically have simple S matrix, so even simpler than in x6 spin chain, which also means that Bethe-Ansatz equations can be solved analytically, which is very important. There is interaction, but Bethe-Ansatz equation can be solved analytically, and this gives big advantage. And then you can compute actually a number of things. And somehow a trait for having simple S matrix is that the Hamiltonians of the toy models are more complicated. So somehow, when you look at normal Heisenberg spin chain, Hamiltonian is very simple. I can write form a little bit later. But S matrix is a little bit more complicated. Bethe-Ansatz a little bit more complicated. Here, what we have is simple physics, so simple S matrix, simple dynamics. But in exchange, the Hamiltonian is maybe a little bit more complicated. And this is the motivation for considering medium-range spin chains. And let me show you one example. So one example comes from the x6z Heisenberg spin chain, actually. In x6z model, we have a coupling constant delta, which is the anisotropy parameter, and then Hamiltonian of x6z is the following. I will use letters X, Y, and Z now for the Pauli matrices, just a shorthand. So these are 2 by 2 matrices. And Hamiltonian is the following summation over now sides J from 1 to L, periodic boundary conditions. So we have X plus Y plus delta times Z on nearest neighbor conditions. So J plus 1, now J plus 1, J plus 1. This is well-known Heisenberg spin chain. And people want to look at transport in the Heisenberg spin chain, which means that for hydrodynamics, maybe you would want to consider the spin transport. So in this model, Heisenberg spin chain, the global spin Sz, which is summations over the Pauli Z operators. This is a conserved quantity. And then you want to consider transport of this quantity. And more particular, what you want to look at is, for example, the 2-point correlation function of spin Z operators. So you put one to 0, 0, and another one to X state. And you want to look at what is mean value of this with respect to some finite temperature ensemble, for example. You can look at other ensembles also, but this is very common to look at finite temperature ensemble. And then based on this quantity, whether or not it shows ballistic terms or ballistic behavior or so 1 over T behavior or diffusive behavior, it is the combination of X and T, you can figure out what type of transport is in the model. And there are some predictions of this by hydrodynamics. Now, how can we prove it? I mean, as I mentioned before, if you want to prove something, maybe you need a more simple theory. And one regime where a more simple theory exists is a special regime where people derive the so-called folded XXA model. I will talk about this model a little bit to give motivation. So the specific regime is that you want to choose a temperature which is very, very large. So it's even larger than the delta anisotropy parameter, but you also choose delta parameter to be very, very large. It's a special physical regime. Maybe it's a little bit artificial, but at least it's a good point where some toy model exists. So this is large delta limit, large anisotropy limit, but you choose temperature even much bigger so that simple things what you would simply compute in this limit are actually become more complicated. Normally, when you do large delta limit, then only antiferromagnetic or ferromagnetic states survive in this mean value, but now temperature is even bigger than delta, so all sectors in the theory survive. And then this model of folded XXA model was suggested to deal with this kind of this regime. It was suggested 2 papers almost at the same time. In this case, group of Maurizio Fagotti was before us, but a couple of months later, independently, we also discovered it. Joint paper with Yufeng Yang, Eric Vernier, Tamás Gombor, Artur Rucaliuk, also Levente Piszczák, my PhD student, and me. So it's a paper with a long list of authors. But it turns out that the model was in the literature even before. So actually, there was a condensed matter group who published it like even two years before us. But later I discovered that some Indians actually had almost the same model in stochastic version, but Hamiltonian was given in the 90s, so more than 20 years before. So the important models are always discovered independently multiple times. And maybe even more discoveries are there, I don't know. So, but I know at least 4 papers which are completely independent from each other and they discover the same model. So what is the model? This would be a topic again for a different talk. So I will not tell you how to derive the model. There's no time. So we need to focus on this regime, maybe this correlation function, and there are multiple ways of deriving the model. I will now tell you what is the model. So the model Hamiltonian of folded XXA is the following. That's again we have a summation of the sides. But now we have a 4-side interaction term. So now I can write it like this, that I write here hopping between, not enough space, hopping between side j plus 1 and j plus 2 in this form, j plus 1, j plus 2. And this hopping is controlled by some state on the neighboring spins, and I will here write 1 plus z at j multiplied by z at j plus 3. So it's a 4-side interaction. What does it mean? I mean, this means that we have 4 sides, j plus 1, j plus 2, j plus 3. And then these terms, they give you hopping. So here particles can hop from left to right, from right to left. because this describes you like hopping exchange of. So it describes you this exchange process of up down to down up. But then this is controlled by something which is here, and what is here is it means you that if the state of the spin series is the same, up or down down, then this gives you a factor of 2. But if it is different, then it gives you 0. So this means that particle hopping here is possible only if the state of this spin to the right and this spin to the left is the same. And it turns out that this model can be derived from mixing the spin chain in this delta limit, at least delta infinity limit, at least 2 ways. But also it is an independent model and it is integrable. So somehow the integrability is not lost. It would be a separate talk. It's a very interesting story. I don't have time. But just believe me for the moment that this is an integrable model. It has an infinite number of conserved charges. But very important message is that for this limit, somehow the usual Lux operator construction of the Hamiltonian does not survive. This is very interesting. So
why do you call this XXG? Because there is no anisotropy.
Yeah, it's just because it comes from. So Mauricio Fagotti called it, and Lena Zading, they called it folded, because they have what they have is some kind of folding mechanism for the spectrum. So it's a historical name. I don't like it. For me, it would be handle deformation of XX, but anyway.
Better ansatz applicable.
Huh?
Better ansatz.
It's known better ansatz, yes.
Oh,
Yeah. But no time for me now. Just believe me that this model is independent now, and it has an infinite number of conserved charges. All of the conserved charges can be derived in a careful limit from conserved charges of this model, but the Lux operator somehow dies within this limit. It's very strange. The reason is that the conserved charges are somehow subleading in this limit of delta coming to infinity. In a very careful procedure gives you them, but the Lux operators become trivial in this limit. So somehow, if you want to have transfer matrix and Lux operator for this model, then you need to start from scratch. This is a message. Believe me, if I would have now 20 minutes, I would show you the details, but it really definitely dies. And this was also.
But Balazs, if you expand the transfer matrix, usually you get the charges. Can't you just put them back to get something like a transfer matrix?
The problem is that the two limits don't commute. So taking derivatives of transfer matrix and this delta infinity limit, they don't commute.
Okay.
And this model was specifically the motivation for us to think about medium range spin chains, because here we have 4-side interaction, so it's definitely more complicated than 2-side interaction. And you can also prove that this model is not in a family of a non-integrable model, because you could ask yourself, is there an integrable model which is nearest neighbor interacting, which would somehow commute with this? Or in other words, is this maybe a charge of a known model, non-integrable model, higher charge? But you can prove with explicit computation that no. So this charge does not sit in any of the XXA models or anything else, okay? So it's definitely a new model. And this was motivation for us to start looking and understand this general structure. So maybe it's a long introduction, but now we understand why we want to look at this model, this problem, also independently from long range deformation.
So it seems that they do contain the nearest neighbor interaction, which is XY model.
Yeah.
So maybe the second term, which comes this 4-side interaction, can be considered as a kind of a conserved quantities of XY spin chain.
So the full product is not in the XY. So it's not a sum. It's a product because it's multiplied.
No. First term, the 1 times this XY is XY model, right? Then you are adding another term, which is a GZXX or GZYY, which is a 4-side interactions.
Yeah.
So those 2 terms may be some conserved charges of XY.
No, but they are not. So we check.
They're not.
But for this, you need to really make a check. Actually, Mathematica, you can do this.
It seems that the coefficients should be very important, right? It's not arbitrary coefficients.
Yeah.
Some fixed coefficients.
Well, actually, there is some freedom here, so you can deform it here with some coupling constant, but let me not go. I mean, the simplest model is this one, yes. Okay, so we need then a theory. So we need a theory how to construct these kind of models, and then I can pose a question, a more general question. So let me think of a model where Hamiltonian is, for example, this form, And then we also know that in this model, there is no two-side Hamiltonian or two-side charge which will commute with it. So let us say that this is the smallest charge, but let us also say that it has higher conserved charges Q alpha, where alpha it is a member of the integers. So maybe typically in these models, there is not a charge for every length, but for selected subset of lengths. But still, we call it an integrable model if Hamiltonian is like this, with let's say 3-side or 4-side interaction, and there exists infinite number of charges on an infinite length swing chain, and this is our setting. And I want to have algebraic framework for constructing integrable models like this, and I also want to ask the question: what are all possibilities for integrable spin chains of this form? Okay, so how can I classify them? How can I find all examples, or maybe it's not possible to classify them completely, but at least if I give some symmetries, then I can make classifications. So I can also tell you that I want to look at models which are SU2 symmetric. SU2 symmetric with 3-side interaction, SU2 symmetric with 4-side interaction, etc. What are all possibilities? And then this should be a very well-defined question with like discrete number of answers. And I want to solve this problem. And the models that we get, some of them are already there in the literature, and some of them are new. And another requirement is very important, that this model should be rigorously, completely translational invariant, which is a nice property. So here there is no staggering, because in the literature there are some cases where you would have some combination of transfer matrices on inhomogeneous spin chains with some staggering, where you would get something similar but with a staggered Hamiltonian. So for each second side, something odd x and even x would have a little bit different Hamiltonian. I want to disregard these cases because I know that some constructions in the literature apply in these cases, but if it is completely translational invariant, then something new is happening. All of the cases in the literature where this staggering idea works, they become more easy and more trivial in the case when this is translational invariant. So this is the setting, these are the requirements that I want to have. And I will start with derivation of Laplace operators, basically, the structure what we need. But I need to review what is happening for nearest neighbor spin chains, because I will modify that construction. So I don't know how much the audience is familiar with Laplace operators and transfer matrices. There's no time to give a full introduction, obviously, but at least I will show you the main formula. So integrable spin chains, we work with Laplace operators. I will use graphical notation. So Laplace operator X is a linear operator which acts on two spaces, typically an auxiliary space and a physical space with index J, and it has some spectral parameter U. So it's a linear operator acting on two sides, so to say, or two spaces. And I will use this graphical notation that it looks like this, for example, that other notation is that I can actually draw a box. So by this, I mean that, for example, this is auxiliary space and this is a physical space J, and then the linear operator acts on these two products of spaces, and then this is outgoing J and outgoing auxiliary space. I can also draw a box, which is notation from matrix product operator literature. So if you look at matrix product operators, then you would see pictures which use this notation. Anyway, it's just a notation for a linear operator. Two incoming legs, like a tensor with two incoming legs and two outgoing legs. And then I construct something which is called a transfer matrix, typically, out of the Laplace operator, which is the product of these Laplace operators in auxiliary space. So the spin chain that I have, I use this pictorial notation that spins live on the lines, and then these are the sides. So this is the side, and depending on how you look at it, but 1, 2, 3, 4, etc. If I draw it like this, and then the transfer matrix which acts on it can be drawn like this. I have the boxes, and I connect the boxes, which means the operator product in that space, something like this, etc. And then this means that this is side 1, side 2, 3, 4, and this is auxiliary space. And I take a sequence of products of Laplace operators. All of them act on the same auxiliary space, but they act on different physical sides in this way. And then the transfer matrix is a trace in the auxiliary space. I mean, I could write down the formula, but I hope the pictorial notation is clear. And then you use Yang-Buster equation for the Laplace operators to show that the transfer matrix is commute. So this also has a parameter U. I forgot it here. So U is spectral parameter for the Lux operator. And then with this, and then you can show that T, U, and TV commute with each other. Or to show this, you use the Young-Baxter relation, which is also called RLL relation in this case, which I can draw picture in the following way, that I have some kind of Lux operator with rapidity U. I act with another Lux operator with rapidity V, and then I do it twice because I will exchange them. So now this will be U. Now this will be V. And then the R matrix is such that here I put an R matrix, and then this is equal to here, when I put here an R matrix. So this is RLL. So somehow it means that LL. Well, I could write out the details, but hopefully those who have seen it already understand what is happening. So here I act with the R matrix on two auxiliary spaces. Afterwards, I act with the Lux operators on two auxiliary spaces and the same physical space. And here I act first with the two L matrices on two auxiliary spaces and one physical space, and afterwards with the R matrix on two auxiliary spaces. And this means that this standard plane argument that if I take product of two transfer matrices, then with the help of R matrix, I can exchange the order of how the Lux operators work, and I can go over the full Hilbert space, and I can also get rid of these traits, which is there in the transfer matrix, and then I show this commutativity. Sorry, no time to explain it. And also, how do you get Hamiltonian from this construction? So to get Hamiltonian, you need actually the so-called regularity condition. So the regularity condition is that, space a little bit less. So Lux operator acting on any two spaces, I will write it like this: 1, 2 at zero rapidity should be permutation operator acting on those two spaces, which means that if I draw it, that if I set to rapidity to 0, it means pictorially that there is just a permutation between the spaces, so it acts like this. So whatever comes here goes here, and whatever comes here goes here. And from this you can derive, when you substitute this initial condition to the transfer matrix, that the transfer matrix at rapidity U will be the cyclic shift operator. I denote it by U, but I could choose anything. So cyclic shift on the spin chain. And with this, you can prove that if you take the logarithmic derivative of the transfer matrix at 0, so you define log of TU, you derive with respect to U, and you take it at U equals 0, then you get something proportional to the Hamiltonian. You can just derive it to the Hamiltonian. And the Hamiltonian density is the following. You delete it and continue later. So the Hamiltonian density on sides x and x plus 1 will be the derivative of an operator called Lux check operator acting on sides x and x plus 1, and also at U equals 0, where the Lux check is simply permutation operator times the Lux. Okay, there is no time to. It would be a separate talk to give all the details, but and this is all depending on you. So now we want to generalize this construction to the medium range cases. So what do we have in the medium range case? We don't have this, we have three-side interaction. And now there is a technical idea which I want to explain to you, namely this grouping of sides together. So imagine that you have your spin chains. Now for the moment I will draw them with not with lines but with dots. So these are your spins. And imagine that you have a three-side operator which acts on triplets. Now what you want to do is maybe you want to make this block spin transformation. So you group neighboring spins into one big block. This means you will get a spin chain with half the length but bigger Hilbert space. So the Hilbert space will be double. It will be the tensor product Hilbert space of two local spaces, so n square dimensional. But in this double Hilbert space, the interaction will be already nearest neighbor interaction. Right? Because here you have interaction between these three spins and also these three spins and then these three spins. But you can see that it's nearest neighbor already for the group spins. Now this means that, okay, nearest neighbor for the Hamiltonian, it will be also short range for the higher charges. So in the double Hilbert space, you have a nice nearest neighbor interacting model. And we believe that in all of these cases, we have a Lux operator and we have an R matrix. So maybe you say that this is completely trivial now, no? I mean, we do this blocking transformation and we look what is the Lax operator here.
What is the Lax operator of this new block spin? What is the Lax operator? The test product of original Lax operator? No. How do you find the new Lax operator?
So stay with me for a little bit. I will go there 5 minutes maybe or something. So, because I want to give the thought of how to arrive. So maybe you would somehow look for these higher spaces and look for all integrable models in there, which is nearest neighbor interacting, and try to find what is lost there. But I'm telling you that this is not a good idea, because if you look at all possible models which are nearest neighbor interacting with these spaces, then some of them will be translational invariant with three-side interaction, but some of them will not be translational invariant. Because this construction of blocking is not translational invariant, because we choose that these two and these two are blocked. And now this gives us the big idea to proceed further. Namely, we want to consider also the other type of blocking transformation. So we want to connect these two also and these two, and then go on. And then we want to require that the transfer matrix which we will get by this blocking and by this blocking should be equal, because then we have translational invariance. And then this gives us a strong condition, and we want to imply this condition to the Lax operators. And this is how to find the Lax operators, and this gives us the idea what to do. And the idea is maybe I will continue here, or maybe I should I don't know. So the idea is that if we do one blocking transformation, then it means that I block two spaces together. This also means that I would need to have auxiliary space which consists also of two spaces, because in all of these cases the auxiliary is always the same as physical space. So the Lax operator, instead of just a simple Lax like here, would be a more complicated object, which looks like this, that it has like many legs now, altogether, I don't know, 8 legs, which means that it acts on two physical spaces and two auxiliary spaces. And I don't specify yet what it is, and it also has some kind of spectral parameter again U. And now the requirement is that I should construct transfer matrices from these more complicated Lax operators for the blocked spins. And it should be such that for the two different blockings, it should give the same answer, the same transfer matrices. And I will draw it down for you so that you understand a little bit better what this means, or hopefully. So I will draw now 6 sides, 1, 2, a little bit more space. I delete it, and I will try to do it here, and then you will see what I mean. Hopefully, this will be the only technical computation that I will do, but it's also not technical, it's drawing, but anyway. So 1, 2, 3, 4, 5, 6, and then for one blocking transformation, I see this. These are auxiliary spaces, 2 auxiliary spaces. Now this is one of the transfer matrices if I also take trace here. And I also want to do a different blocking, but use the same Lax operator. So I do also something like this, for example. So now Lax operators act on different pairs, and I have periodic boundary conditions for simplicity. So this is something like this. So I want to require that the two operators are the same. So how can I do it? And we don't have a really rigorous proof that it is always like this. We can prove it under some conditions, but I tell you the answer. So the answer is that we should have factorization of this object, factorization in the following form, that this should be equal to product of two Lax operators, which act on two physical spaces, two auxiliary spaces and one physical space. Because if this big object factorizes like this into product of two Lax operators of the same type, then when I substitute this factorization into here, then it's the same.
Wait a minute. So can you draw what is inside of these blocks? So just the lines, the single line crossing with 2 lines.
We don't know yet. So this should be found out.
But there is already this instant map. There is some called the fusion model.
Yeah, this is different. Yeah.
Different, I'm sure.
Yeah, we checked. Because for the fused models, you have commutation with some previously known Hamiltonians and charges, so we chose, yes.
I'm not sure. I mean, is the control charges are related? Because there is internal sum, so it's not really obvious.
So
No,
does
no.
this new object satisfy some Young-Baxter equation, like a fused R matrix or not?
It satisfies, so, but let me draw it, because now we will have bigger matrices. But it satisfies Young-Baxter relation, yes. So, and so far I haven't told you anything about what is concretely in the boxes. But now the R matrix is bigger, so R matrix will
The
be.
point is that usually express this block in terms of single lines. Because
No, no, no.
you should connect with the previous model.
No, I should not. So that will be my point, because what you have in mind is something where this is also factorized further, that this is factorized into something like this, or maybe with projectors here.
Yeah.
But we have arguments and we have proofs that in the new models this cannot be done. So sometimes
Yeah, maybe some other manipulation you can add it, but my point is that it should be written in terms of single line model.
no, it should not. I mean that's the whole
Then
point.
why you started from the beginning some known integral model?
I mean, so that was I want. So yeah. So I want to move. I want to look at this model, which is on its own right, because I have reasons to show that all higher conserved charges cannot be found anymore from a Lax operator of this model, because taking derivatives and delta infinity doesn't commute. So it's good to forget the original models, because I don't want to look at the new model as deformation of the original one.
Okay, I can. Yeah, please. Correct.
And coming to the question of Zoli, so these objects also satisfy Young-Baxter relation. I can write the formula, but for me it's easier to write picture. So it is like this, that this has U, and then this has spectra parameter V, and then this will commute. So now the R matrix acts on 4 spaces. It has parameters U, V again, and then this will give you a commutation. So intertwining relation like this, that now here I have V, here I have U, and then R matrix acts here. So the R matrix will be of double size. R matrix will be actually the R matrix corresponding to these big blocks. So if originally the R matrix was of size n squared times n squared, then now in these models it will be of size n to the 4 times n to the 4. So for spins it will be already 16 by 16 for qubits. And it satisfies Young-Baxter relation. So in our new examples we show. So in the new example that we found, you can actually see that the R matrices are actually solutions of Young-Baxter equation, which are new solutions sometimes. But sometimes it was figured out that they belong to some known classifications. It depends a lot. So this is a difficult issue to figure out whether it was known or not in the literature. For example, for this specific model, for the elliptic Xavier, the R matrix, or maybe not for this one, maybe for the very closely related model, and then Andrei Liashik figured out that it was known in the literature in some obscure paper that people don't know very well, and then, okay, I mean, so, but anyways, our model gives, in principle, new solutions to Young-Baxter equation. Sometimes it is known, sometimes not. And then what is Hamiltonian? So now we also need the regularity condition in this construction, and the regularity condition is the following, that at spectra parameter 0, this object should be also a permutation, but now in a little bit different way. So at U equals 0, it should be a permutation like this, that this is permuted here, this is permuted here, and this is permuted here. So these two auxiliary spaces are permuted such that this becomes to the physical space, this becomes to the other auxiliary space, and the physical space becomes to the first auxiliary space. If you use this initial condition, then you can check that actually the three-side Hamiltonian, where is it? I forgot x plus 1 and x plus 2. This will be actually the derivative with respect to u of a new Lutz-Check operator again. But the new Lutz-Check operator is a three-side operator. It's almost the same as the Lutz operator here, which acts on 3 spaces, but you need to add this inverse of this permutation again. So something like logarithmic derivative again. And then this is the basic construction. Maybe it's a little bit mysterious now because I don't have examples, but let me tell you the methods for classification. And then maybe I could also tell you examples, but maybe that is less important, because in any case, if I tell you example, then a lot of computation should be done to check that these things actually work. But what about classification? So, and this will be my last topic, I mean, very, very briefly. Classification.
Sorry about that. Is the folded XXG also periodic boundary condition?
Yeah. So, and this is a little bit even more complicated because we have four-side interaction, but you can transform this into a three-side interacting version, and then this applies immediately. So classification, and maybe some of you know, if you have neither stable interacting spin chains, there is something called the Reshetikhin condition, which is attributed to Reshetikhin, either though it's in neither of his papers, but maybe he said it somewhere, I don't know. So the idea is that you should have a Hamiltonian which commutes with a Q3 three-side charge, such that the Q3 should have a very specific density. So operator density of Q3 should be commutator of Hx with Hx plus 1, and maybe plus another charge, which is also a two-side charge positioned at X. And it turns out that if you can find Q3 with this H tilde, such that it commutes with the two-side Hamiltonian, then it is integrable, and then you can find these Lax operators, etc. And this is not proven, it is a conjecture, but so far there is no counterexample. So one way you can prove it, so if you have Yang-Baxter relation, from Yang-Baxter relation, you can prove that Hamiltonian commutes with Q3, but this Q3 is of this form. This is a proof. So one way proof is good. This guy is zero if R matrix is of difference form. If R matrix is of non-difference form, then this is non-zero. For Hubbard model, this is non-zero. But this is also two-side charge. Now, the other way around, this is not proven, but all examples show this, that actually I have a twisted counterexample, but that's a... So all physically important examples show that if Q3 exists with this density that it commutes, then there is a Lax operator also in solution. Now we generalize this condition, so we figured out what is the Reshetikhin condition for our models, and now what we have is the simplest following, that Hamiltonian, which is a three-side operator now, should commute with the five-side charge Q5, where the density, operator density of Q5 is the following. So I should take commutator of Hx with Hx plus 1 plus Hx plus 2, and perhaps I can add the H tilde with, this is also a three-side. So the full object can be five sides. This commutator can be non-zero, and it spans five sides. And our statement is that if this construction exists, so if there is a Lax operator which satisfies RRL relations, then this can be proven. And the second thing is that this condition can be used to figure out solutions to classify models, because similar to how this is proven in the literature, or not, this is used in the literature, we can look at these equations, and solving these equations is simpler than solving Yang-Baxter. This is a statement. Because somehow, you see, for example, if you assume that this is zero, then this equation is just a cubic equation in H. But it doesn't have spectral parameter, it's algebraic equation. Much simpler than Yang-Baxter, because Yang-Baxter has a spectral parameter. And similar to this, in the simplest cases, this is zero, and then this is cubic equation still in this three-side H. And we can use it to classify Hamiltonians with certain symmetries. And if we have these guys, then it's just linear in these guys, so it's still relatively mild. And we performed this classification. So, for example, we showed what are possible models with FQ2 symmetry with three-side and four-side interaction. Very briefly, results. So for three-side interaction, we didn't find any new model. But if I have a four-side interaction, then it turns out that we actually found a new SU2 symmetric model. We don't know what is its solution. It should be solved by nested beta ansatz, but it's a nice spin-on-half model with four-side interaction. Okay, I don't know. Maybe it's not relevant for anything, but we figured out it exists. So that's a new result. We also looked at U1 symmetric cases. Then there are more models. We did a classification, and we also considered other constraints. So generally, if you just say what are all possible integrable models, then already solving this equation is too difficult. So we did these classifications also with Mathematica. Maybe we were too lazy, or I don't know, too stupid or something. But anyway, Mathematica helped. But for the general case, even these equations are too difficult. So So we don't have a full arbitrary classification, but with given symmetries, we could classify the models. And for these models, we also computed lots of operators and then matrices. So these objects, what are given here, really believe me, they exist. And in the paper, you can find formulas. I don't think I have time for that. And we should come back really to this question of chunk beams, because it's always asked from me in conferences. So how did we really prove that this does not come from fusion somehow? And so let me really remember, because so for example, one of the arguments is that if you do this from fusion, then it cannot satisfy this regularity condition which is needed. So the fused transfer matrices don't give you a three-side interaction. That's my argument, one. But other arguments are that you should be able to see commutation relation with some charges, maybe not precisely the same ones which are in the fused models, but some smaller charges. And in our models, we could really see that there is no smaller charge than these guys. Okay, and I think with this I will wrap up. So very briefly, physical message. So physical message is, this is a nice technology. We can find examples. What is it good for? Let me summarize. It is good for because we can prove integrability of logarithmic Zig at all charges, etc. We can construct new integrable models. It's also very good. But the third, maybe most important, at least for this audience, is that maybe we can use this idea, these constructions, to go to the long-range deformed models, where we could solve this problem of wrapping corrections. And this is most important. And this is a paper of my postdoc, Tamás Gombor, which appeared like in June or something, where he does first steps towards this goal. It's not solved. Of course, for ADS CFT, it would take a lot of work to solve, but no wonder, it's a complicated issue. But Tamás did some important steps, and he could compute some wrapping corrections in some simplified toy models. So I think that's a considerable progress. And it is all based on these ideas, what we did here. Enlargement of auxiliary spaces, etc., etc. Yeah, thank you.
Okay, thank you, Balazs. So are there any questions?
Yes, so forget about this fusion.
Yeah.
Actually, about 30 years ago, I also proposed a way to construct the non-local long-range spin chain, integral spin chains based on Gonzaga algebra. So, and also I found this medium range integral spin chains of the C2, even higher algebra, etc. So I don't know whether there will be some overlapping, but
you should tell me, show me the.
Yeah, I can.
Okay.
So I hope there's some overlap, but of course, this is not relying on any Young-Baxter type theories, but this is basically generalization of this Gonzaga's solution of the Ising. Are you sure?
And are they also free fermionics or spectrum or?
Yeah, I can find the spectrum.
But is it free fermion or?
No, it's not. Because it's a also it can contain some arbitrary parameters in the terms, and so it depends on those parameters.
So are there other
Balazs,
questions?
if you don't use a projector in the fusion, then the regularity condition is satisfied, no?
Yeah.
If you go back to this picture and then imagine that this two block is just the product of two one blocks, and each one block satisfies the regularity.
Yeah. Yes, but then you also get the normal Hamiltonian back.
Yeah.
So normal two-side Hamiltonian. So that's why it's a little bit trivial. So yeah, indeed you can do that also, but then you don't move away from two-side interaction.
Yeah, I think the key point probably is that your 2x2 or 4x4 R matrix, this is what would be the bond state R matrix. It's not the bond state R matrix. It's something new.
Yes.
Yeah. So about Reshetkin condition. So in a quantum field theory, if you have one higher spin charge, then you can actually show factorization and then integrability. So can't you do something similar here?
I don't know. I mean, it is similar in spirit, because this also tells you that it is enough to have two charges, or one extra charge on top of Hamiltonian. And what I'm telling you is that this is enough, but okay, we also need this special structure, but more or less, morally, it is the same, that one extra charge is enough to prove integrability completely, infinite set of charge.
Yeah.
But what you are saying is about already the solution where you know the particle content. And this is for spin chains even more general, because this is valid also when U1 symmetry is broken, for example, XYZ spin chain. So in cases where you don't even know what is beta ansatz. We actually have some models. I mean, I could find the Hamiltonian, I don't know it by heart. So we have some models in this class where U1 is completely broken and we don't have any idea of what is beta ansatz or how to solve it. I mean, really, it's completely different from all things what we have seen before, but we know that the condition can be used to figure out logs, and we know the logs, etc. So it's more general. It does not rely on simply just the factorization of S matrix.
I see. Okay.
And I think that Marius Deleuze, so this method was initiated, so this method is very old. Attributed to Reshetkin, but maybe the first paper when it was called Reshetkin condition, maybe it was by Mato, what was it, Grabowski and Mathieu, but maybe even earlier papers attributed to Reshetkin, I don't know. But let me say that this was used in even old times. So this idea to classify models was, for example, who is this guy? Somebody who is not very known because the name is, maybe he did different stuff later, but there was one paper where they classified nearest neighbor SU2 symmetric models for higher spin, and based on this condition. So it's not an old idea, but more recently it was revived by Marius Deleuze and collaborators, like a couple of years ago. And maybe the most important new addition of Marius Deleuze was, I hope he can agree with this, that they said that, okay, now we have Mathematica and we can put this equation to Mathematica. So, because it's much more powerful, because you can play it with hand. But what I'm saying is that many decades ago, people already played it by hand on paper. But now we can do also computer algebra, and much more solutions can be found. So it's like an industry of producing non-equivalent solutions to Yang-Baxter equation. This was initiated by Marius Deleuze, and so we joined to this. So I was also motivated by his papers, and then we joined to this somehow. That's what I wanted to say. That is essentially the new. And I can also say that there are one or two papers where people still do classification of these solutions by hand. So maybe Riviere or I forget all the names, but there was somebody also. So from recent times, a couple of years ago, where they classified all possible 6-vertex-like solutions, and very surprisingly, the paper had new results. So maybe even with 6-vertex or 8-vertex, I don't remember precisely, sorry, but I can find the paper. But some people still do classification on paper, but in the papers of Marius, it was more on Mathematica.
I have one stupid Bible question. So from the naming folded, and also that graphical representation, so isn't there any relation between this folded XXG and open spin chain? So double law there.
Not really. Because you can also find open boundary conditions for these models, but so again we can show that. So this is different from the double row. It's reminding because it has you have these two lines, but it's different. So because in the double row transfer matrices you get for the bulk you have the nearest neighbor interaction, and then here we have something else.
So are there any other questions? If no, let me ask a question. So Balazs, when you talk about this classification of higher spin, do you have Tom Kennedy in mind, who did something like in the 91?
I can look it up.
That's one thing, and another thing is now you have this algebraic construction of this medium range models. It means that you can find the legs and then construct the monodromy as usual, right?
Yes.
So in the usual algebraic beta ansatz, there are two parts. One is how do you get these conserved charges by expanding the transfer matrix. The other is actually using these matrix elements of monodromy matrices to build eigenstates. So what is the status of the second part of the story?
It's completely open.
Okay.
So, you know, even in our common paper on folder X6A, we didn't touch this. I mean, it's already if I can tell the others, like sections, I don't know how many sections, 12, no, more, 13 sections plus conclusions, because we treat different dynamical properties of the model, and then we already stopped, so that's already quite a big paper. And afterwards, Tamás looked a little bit into this, but he was not satisfied, so for folder X6A, some problems arise, and for other models, it was never considered actually, so this is completely new area, but you would need a good motivation to select a specific model and to work on these specific models. For example, so we have this SU2 symmetry four-side model. If you want, I can cook up find the Hamiltonian, but anyway, so it's a nice model, but we don't have any motivation why we want to solve it. So okay, one more integrable model, but if it's not related to anything, I mean, okay, maybe you can solve it, but then you have one paper which will have maybe 2 self-citations, but no citations from anyone else in the world, and then okay, maybe you are not motivated to do it.
So
but
I mean, yeah, even as a matter of principle, you would like to learn at least how this medium range interacting spin chains can be solved algebraically, right? I mean, there might be some general structure there, so I don't agree that this is just a trivial thing. Yeah.
But
anyway, okay.
If you want to do something like this, then you have a good idea of which model to select. And actually, for folder X6A, I still have important questions here. But again, topic for different talk. But this Hilbert space fragmentation is still actually open a little bit. So maybe you remember we discussed with Eric Verdi also, but in the emails you were also included about the spectrum generating operators. So what are those operators which jump from one beta state to another beta state, which lie in different sectors? And this is not solved. And maybe some ideas from those operators, etc., could be useful. I mean, we are working on it. So my PhD student Bosch is working on it. Let's see what we find. So there are selected physical problems where this could come up. It's not about constructing the beta states, but in this case, operators which would jump from one beta state to another state between degenerate states.
Mm-hmm.
Any numerical way to try to solve numerically? Small error and
yeah, we compare the beta ansatz solution and spectrum, and it works. And I mean, for selected, so for this specific model, we know the beta ansatz, but we know it because this is still coming from this phase.
I see. That's why.
But we actually have a different solution also in terms of domain walls, etc. So first idea was this, but then we have a second solution. We checked it works.
You can construct eigenvectors. Or?
Yeah, for this one, yes. And it's very highly degenerate. So this is Hilbert space fragmented. It's an example for so-called quantum Hilbert space fragmentation, and it splits into many sectors which are disconnected kinematically. And within each sector, we know it's integrable, and we know beta ansatz, and between different sectors, it has many degeneracies. So typically here in this model, every state, every energy level is exponentially degenerate, but with what exponent depends on the specific particle content. So it's not like homogeneous, the exponential degeneracy. Some states are twice degenerate, and some states in the middle of the spectrum are exponentially degenerate after Hilbert space dimension or something.
Is it interesting for some application, like some condensed matter system?
Yeah, this is I noted at the beginning the spin transport. So diffusive. So what is very interesting is diffusive spin transport in the delta infinity limit, but also at infinite temperature. So temperature should be even bigger than delta. And we know that spin transport is diffusive from numerics and also hydrodynamics. What is more, you know that, from hydrodynamics, you know that spin diffusion constant is actually a known number. It's this number, it's a numerical number in this limit. And you want to prove this numerical number. We actually have a project for this, but we don't have the proof yet.
By the way, this is a paramagnetic spin chain or anti-paramagnetic? Anti. So some excited states is in terms of some holes.
Yeah, domain was actually in this limit. And in this limit, you can prove rigorously that this model describes you the diffusive transport, more in physics proof, so to say. And then you would want to look at transport in this model because this is easier than the original XZ. So we are doing it. That's not finished yet. But it's nice because so spin diffusion is already a many-body effect, which is very composite and very difficult. And in a specific limit, you get a fixed number like this. So then you are really motivated to compute it. It's a nice number. So the volume of the sphere for some reason, but we don't know why. And okay.
Okay. So in the interest of time, I think we shall move to the next speaker. And before that, let's thank Balazs again for two very nice talks.